lovely humans. It's nice to see you today. We're going to talk about differentiation rules today. So first, these are shortcuts, so you don't have to use the limit definition of a derivative. We're going to use the shortcut. So you still have to know how to use the limit definition of a derivative. Cool. But not for today. Okay, so the derivative of a constant is 0, because remember, a derivative is all about how our function is changing. So if we look at the function here, this constant line, what's the rate of change? How are we changing from 1 second to the next? Well, it's not, so we're not changing at all. Okay, so no change in y values. So the constant must be 0 because the slope is 0. All right, so some examples. Find the derivative of the function using the constant rule. So we write this as, I'm going to take the derivative of y with respect to x, okay? So it means that x is the variable. And what that means is that we're basically taking the derivative of 7. So 7 is a constant. What's the rate of change of 7? It's 0. The derivative is 0. Another way to write this is y prime is equal to 0. Remember, prime means derivative. Okay, so f of x is equal to 0. So I can write f prime of x, the derivative of f. Okay, at 0, I'm going to graph 0. The rate of change of a constant line is still 0. All right, the power rule. So the power rule, remember, it decreases this is for any polynomial function. We're going to take the power of the polynomial, we're going to decrease it by 1 and multiply by n. So it looks like this. So if I have the function x to the n power, we're going to multiply by the power, and then the x's power will be n minus 1. So we decrease the power by 1, and we multiply by the old power. So a fifth degree polynomial, x to the fifth power, so we say f prime of x is equal to, we bring the 5 down, so it becomes a multiplier, 5x to the fourth power. So a fifth degree polynomial will have a rate of change that is a fourth degree polynomial. The next one. These are tricky. We don't like, well, I don't know if you don't like, but whatever. We're going to write this as x to the negative 2 power instead of 1 over x to the second, because now I can take my power, multiply it into the front, so we give me negative 2 times, okay, n minus 1. So negative 2 minus 1 is negative 2x to the negative 3, which is equal to negative 2 over x to the third power. So f prime of x, or the derivative of f, is negative 2 over 3 to the, over, negative 2 over x to the third power. Lastly, let's rewrite our root, our radical, with an exponent. So x to the 2/3 power. So f prime, we multiply by 2/3. Then we decrease our exponent by 1. So 2/3 minus 1 gives us negative 1/3. We can rewrite that as 2 over 3 times x to the positive 1/3, which is 2 over 3 to the third root of x. All right, so honestly, any of these would work, but you need to be able to simplify all of them. All right, the constant multiple. Really, it's the same rule as the power rule. We just, if there's a number already in front of our function, so a constant, a scalar, multiplying our function, then we need to multiply our power by that scalar. So f of x is equal to 3 times x squared. We're going to take the derivative, so we need to say I'm taking the derivative of, we multiply 2 times 3, giving us 6. X, decrease the power to 1. All right, the next one. Let's rewrite this with the power. so x to the, in the numerator, so x to the negative 1. I get y is equal to, we do 1 times 2, which is negative 2, x to the negative 2. Y prime. Y prime is equal to negative 2 over x squared. Last one, let's write with a fractional root or a rational root. So 3 times x to the 3/5. We're going to go ahead and apply the power rule. So multiply 3 by 3/5, giving us 9/5 times x. We're going to subtract 3 over 5 minus 1, giving us negative 2/5. And then let's write that with a positive exponent. So the x comes to the bottom, giving us x to the 2/5. You can also write this, I guess, as 9 over, well, this is all math. 9 over 5 times x, the 5th root of x squared. Okay, so all of these are legal. Okay, the sum and difference rule. So if I have two functions, f and g, that are being added together, as long as both are differentiable to begin with, then we can split these up by taking the derivative of f plus the derivative of g. And same with if we subtract. So we're going to pretend, we're going to say that x cubed, x squared, and 2 are each different functions. So x cubed plus x squared minus 2. They can be each a function on their own. We're going to add up all of their results together. So in the end, so what we do is if we have terms being added or subtracted together, we just apply the power rule to each. So the derivative of x to the third power is 3x squared, plus the derivative of the blue is 2x, our power decreases by 1, minus 2 is a constant, so it's minus 0. So we have f prime of x is equal to 3x squared plus 2x. All right. Again, we have terms, we have a polynomial. We don't have quite a polynomial, but we have terms here. So I'm going to rewrite this as 3x to the 5th minus 2x cubed plus x to the negative 1. We know how to deal with derivatives so far if the base is x and it's being raised to some number power. It can be a fraction, it can be a negative, but this is what we know how to deal with so far. Okay, so I'm going to take f prime of x is equal to, we're going to apply the power rule to 3x to the 5th power, so 15x to the 4th. The next term, 2 times 3 is negative 6x. Reduce the power to 2, plus, we're going to multiply by negative 1. And then we get x to the negative 2. So rewrite this, f prime of x is equal to 15x to the 4th minus 6x squared minus x over, minus 1 over x squared. So bringing that x down to the denominator. All right. Couple more derivative rules. The derivative of sine is cosine of x. We did that last year. And the derivative of cosine is negative sine of x. And I gave you guys a little way to remember this. So in trig, remember that cosine x is positive on the horizontal and it's negative on the horizontal. On the y is defined by sine x, and then in the third on the lower axis, the negative y-axis, sine is negative. So what I can do is, that's kind of how I remember where those go. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine. And the derivative of sine is cosine. And then we start again. It's kind of like powers of imaginary numbers. It all just like goes in a circle. Okay. So find the derivative of 2 sine x. So I have a scalar of 2 and then the function of sine x. What is the derivative of sine x? Well, the derivative is cosine. So I'm going to take the derivative of cosine and multiply by my scalar. So f prime of x is equal to 2 cosine x. Next up, I have a scalar of 1/2, so I have y prime is equal to 1/2 times the derivative of sine x. That one was boring, sorry, is cosine x again. Last one, you should try this one on your own for sure. G prime is, okay, what do I do here? I have pieces being added together, so terms. Can I take the derivative of x? Yes. What's the derivative of x? It is 1 x to the 0 power, which is just 1. All right, so that's just 1. And then a second function being added to x, cosine x. The derivative of cosine x is negative sine x. So I get g prime of x is equal to 1 minus sine x. All right, horizontal tangent lines. So I am going to give you a little graph like this. Yeah, that's good enough. Okay, so where on this graph of f of x, where is the slope or the rate of change 0? Well, the rate of change is 0 at the maximums and the minimum points. Okay, so when I take the derivative, remember derivative is just defining the rates of change. So what I'm going to do is set the derivative equal, I think this has to be setting for grammar purposes, equal to, wow, try again. All right, we're setting the derivative equal to 0. Because why? Because the derivative is the rates of change of the function. So over the whole function, it's its rates of change. So for number 1, we're going to do we're going to take the derivative because I want a function that describes how our original is changing. So our original is changing by, take the derivative, I got 3x squared minus, this is x to the first power, so minus 4, and then the 5 is a constant, so that's going to become a 0. All right, so this defines our rates of change for x cubed minus 4x plus 5. And now, if I want to know where the rates of change is equal to 0, okay? So 0 is equal to 3x squared minus 4. Now I'm going to solve for x by adding 4. Get 4 is equal to 3x squared divided by 3. I get 4 thirds is equal to x squared, square root. X is equal to plus or minus the square root of 4 thirds, or x is equal to plus or minus 2 over root 3, or rationalize. So x is equal to plus or minus root 3 over 3. Well, that's a number we like. Okay. All right, so that means that on this graph, we will have a minimum or a maximum value at plus or minus x, when x equals plus or minus 2 root 3 over 3. All right, next up, let's find the horizontal tangent lines of 0. So thinking horizontal tangent lines are rates of change. So we're going to have to find a derivative, because derivatives tell me about rates of change. So what's the derivative of negative cosine x? Negative cosine x, I can take negative 1, and then what is the derivative of cosine x? The derivative of cosine x is negative sine x. So I get f prime of x is equal to positive sine x. So take our derivative, set it equal to 0 to figure out when the rate is 0. Okay, so sine x, we solve by doing sine inverse of 0 is equal to x. Oh, in calc, we're always in radians. Don't listen to Miss Stewart. She makes you switch back and forth. But in calc, we're always in radians. Okay, so sine inverse of 0 is equal to x when x is 0 radians, pi radians, 2 pi radians, like on the x-axis here. Okay, so, or we can say pi n, where n is equal to any integer. Remember this? Yeah, it never goes away. Okay, I'm going to do the second part of the video.